So although quite fair, our description of the two-telescope interferometer and the data it outputs did make a few idealizations that we're about to account for in this section on the processes and the phenomena that affect interferometric measurements. The starting point of interferometry differs significantly from that of traditional astronomy. A traditional astronomer indeed uses an image as a starting point and is going to analyze this image to extract quantitative measurements about the target of interest, be it a separation between objects or a relative brightness between objects that is then going to use to provide a physical description of the object of his interest. An interferometrist has a very different starting point. He begins with individual interferometric measurements that by themselves mean very little, that can then be combined together to produce a good description of a certain region of the sky. The description can result in producing a picture, or it can also result in producing the same type of quantitative measurements that the astronomer extracted from his image. The measurements we're extracting from interferometric observations are measurements of a quantity that we've introduced on several occasions now, self-coherence. It is a complex number made of two parts. We have a modulus and we have a phase. The situation is somewhat similar to that you're most familiar with when you're about to weigh yourself on a bathroom scale. Only instead of trying to measure the weight here, we are using our scale, our interferometric scale, to measure the coherence properties of a given target. The analogy with the scale is actually quite useful because we don't necessarily agree with the result we see on the dial of the scale, and one reason may very well be that the 0 point of a bathroom scale was not properly set, and we typically use a little dial here to first step down from the bathroom scale, set it to 0, and then step back in to see if we actually are the way we first measured in the first place. It turns out that there are several parameters in practice, observing conditions or details in the implementation of my instrument that are going to affect the accuracy of the measurements of coherence. And so it's going to be very important to understand what processes and what phenomena may result in inaccurate measurements and how we can address those things. The same way, there is a second part to this analogy. The fact that the dial on our measurements here can only cover a finite range of weight. And no matter what the target, the modulus and the phase have to be values that are bound between two values. For the visibility, it's a positive number that is constrained, that has to be contained between 0 and 1 and cannot extend beyond those values. The same thing goes for the phase, which can not be any, which is bound between the values of 0 and 2 pi. And when you are faced with measuring quantities that are bound between these kind of values, the precision with which you're going to be measuring those parameters is going to be extremely important. Your capacity to be able to make a difference at a percent or a 1 per thousand level is going to be really critical, and it is going to set things like the dynamical range of the image you're going to be able to produce, or have a very strong and direct impact on the precision associated to the properties, the quantitative properties like angular diameters, angular separation, contrast ratios you're actually trying to derive from your observations. These two things, accuracy and precision, are really essential. They are like we've seen and like we'll see, several phenomena, biases, instabilities, computational errors that all conspire against you and alter the estimation you can make for the measurements of coherence. And so our job in this section is really going to be understand those phenomena and do our best job, the best job possible in order to account for them and produce the most sensible and the most representative measurements for later inquiry.